wrap up, and then we'll have a good discussion from now onwards. I think some of the issues um, are sorted out. Okay, are you able to see my PPT slide?
Yes, sir.
All right. Okay.
Yes, sir.
All right. So what I'm doing is that I'm presenting the entire screen. So I have moved all those things that are required onto my other devices, so that I can just use it for presenting. Now, so we started off with some terminology, and then okay, so we were here. So we are about to introduce this four terminology, and then we stopped there. Okay. Now let's say these are two plates connected with a set of bolts. Okay. Now the center dotted line is the junction of those two plates, and over that there is a cover plate. Okay. Typically, in both sides we'll have for symmetry. Now, so on each side of that center line we have eight
Sir,
bolts arranged.
sir, kindly present the full screen, sir, because half of them is blurred on. So if you share.
If I present the full screen, I don't have the maneuverability, sir. That's why I shared the entire screen.
Okay, then you can the screen. This one, sir, you can maximize the screen as much as possible.
Yeah,
But-
Right share.
okay, maybe I can hide these things,
Yes, yes, yes,
right?
yes, yes. That would be better.
That would be right, isn't it? Okay.
And the slide sorter also on the side. Can you hide the?
Okay,
slide?
okay. This one, yeah.
Yes, yes.
Correct.
Leave it.
Yeah.
Yes. Yeah, you can do it.
Yeah, that can go as much as possible.
Yes.
Right.
Yes.
All right. Now, these terminologies, like we have pitch and gauge. These are the two important things. And edge distance and end distance are something that you have to always have it in your no these four. And in fact, you should always have in your fingertips, especially if you're becoming a design engineer. Uh, so pitch is the distance between two bolts. Okay, in the direction of stress. For example, now let's say I have applied force in this direction, and then force in this direction. Okay. Now, in the direction of force, what is the distance between two bolts? That's called pitch. In the direction perpendicular to the direction of force, if you measure the distance between the bolts, that's called edge. Sorry, gauge. Now, of course, the bolts cannot be placed right at the edge of the plate. So we'll have to have some kind of a minimum clear distances, like you have it in any case. Like let's say in concrete also we have the same thing. You can't place a bar, right to the edge. So we should leave away some kind of spacing. So the distance between the end of this plate, okay, and the one row of the bolts is called end distance. Okay, the distance between this line of bolts and then, okay, let me mark. Okay, this is the one edge. So this distance is edge distance, and this distance is end distance. Okay, so end distance is again in the direction in the line of action of force, and then edge distance is in the line perpendicular to the action of the force. Okay. Now, having understood, I hope you got the meaning of these four terms. Are you with me?
Yes, sir.
Yeah.
Yes, sir.
Okay. So, having understood these things, let's take up the real problems in this section. Not the problems. I mean, straight away, we are going to understand some basic again some theory, and then see. All right. Now, obviously, as we see, we are always going to design this joint, okay, with some bolts to resist some load P, okay, some load P, okay. Now, obviously, this load P shall be shared by all these bolts, okay. Now, whatever that shear that's going to come onto these bolts, shall not be more than the a specific term, a specific capacity of the bolt. Okay, right? That's called bolt value. We will define what is this bolt value. Okay, in a typical case, let's say all the bolts are equally sharing this load. So that supposing there are, let's say, eight bolts here, okay, on one side of the joint, p by 8 shall not be greater than the bolt value. Okay, then only it is safe. Now what is this bolt value? It is nothing like capacity of the bolt. Okay, now when you are talking about in the ways in which a bolt will carry the load, okay, we discussed about certain aspects. We said it's going to resist the load by bearing, shear, or tension. Okay, well, I guess we didn't talk about tension, right? So can someone try to come up with a situation where a bolt will carry the load by tension? Any specific example that you can think of?
When bolts are used in stanchions due to
Stanchion.
uplift.
Due to uplift. Perfect. Yes. And also when you have this HSFC bolts, okay, wherein that load transfer is primarily through the friction, but again that will get converted to tension alone. Correct?
Yes, sir.
Yeah. So because there is no bearing or shear there, it's only the tension which is getting transmitted through the friction. So there also tension strength of the bolt shall be evaluated. Now let us look at these three terminology, these two strength of the bolts, and then come to a definition of what's a bolt value. Now the first one that we are going to see is shear strength of the bolt. Okay. Okay. So when you are trying to write on these digital devices, you become suddenly a second grade or third grade student because the handwriting becomes so bizarre. Now, see what we have is actually there are two critical terminologies that we have to always remember. Okay, these things will keep coming, so I'm going to repeat: nominal and design. Okay, so when you say nominal, it is some kind of a gross. Okay, but it's not effective. Okay, some kind of a gross. When you say design, okay, there is a factor involved here. Okay, now let's say V and sorry SB is the nominal shear strength of the bolt. Okay, we have VDSB, which is VNSB divided by some factor of safety. Okay, this is a preliminary concept that we have learned in the limit state design, isn't it? So we always want to take care of any kind of risk involved in getting this strength through this factor of safety. Maybe the manufacturing of the bolt is not so consistent. Okay, maybe we will not be able to guarantee that quality all the time. So any such kind of um, risk or possibility of losing the strength will always be taken care of through these factor of safeties. Now, having defined what is design strength and nominal strength, now let's go to nominal strength. Right. So we are talking about shear strength of a bolt. So nominal shear strength of the bolt, sorry, VNSB is equal to, let me write it and then I'll explain the formula. FUB divided by root 3 into NN A and B plus NS A S B. Okay, now let's see. So when you're talking about shear force, again, force is always something like stress into area, isn't it? So we have some quality which is similar to stress here. Okay, this is FUB by root 3, wherein FUB is ultimate tensile strength. Can someone tell me how do you get the ultimate tensile strength? Just give a guess.
Multiplied by the factor of safety.
Come again?
Multiplied by the factor of safety.
No. See, ultimate tensile strength is the highest point on the stress strain diagram. Okay, when you get the stress strain diagram from the UTM testing, in actual testing, the highest point is that FUB. Okay, so as we said, shear strength is going to be always less than the tensile strength. So we are taking a factor of root 3 to get the shear strength. So this FU by root 3 is some kind of a shear strength of the material. Are you with me?
Yes.
Yes, sir.
Yeah. Now,
Yes, sir.
now, after the stress part is taken care, now we want to find out, we want to understand what is this area part. Okay, NN into ANB plus NS into ASB. Okay. Now, when you have a ball, typically the threading is typically only up to some required length. Okay, we don't want to provide the threading throughout. Okay, the reason being, when you provide a threading, obviously you are going to take off some material. Okay, so that will actually decrease the net section area that we have. So this we are talking about shear. So a shear plane can pass through this area or pass through this area. Okay, so this NN is the number of shear planes passing through the threads. Okay, NS is the number of shear planes passing through the area where there are no threads. Okay, for example, let's say we have we'll take this situation. We have a plate like two plates like this. Now I have two cover plates. I have a bolt. Okay. Now, can someone tell me what kind of a shear mechanism that's going to act here? How many shear planes will be there when you have loading like this?
2, sir.
2. Okay. So there will be one here and then will be one here. Now, let's say this bolt has threading throughout. Okay. Both the planes will be passing through the threads, isn't it? If you have threading only up to half, up to this, so there will be shear plane, one shear plane passing through threads, the other shear planes will not be passing through the threads. Okay, so depending on the scenario, we should be able to choose what is the number of shear planes passing through threads and not passing through threads. Okay, now I'll come to this A and B and B and ASB. So what we are saying, A and B is the shank area. Okay, shank area is the cross section of the shank without any threads. Now, A and B is the area of cross section at the threads when you have threads. Obviously, it shall be less than the shank cross section area. So typically, you can approximately take it to be 0.78. Otherwise, you can choose from the steel tables. This information also will be given to you. Okay. Other, in the absence of such data, you can take it to be 0.78. Now, let me ask a simple question and then try to understand what are this AN and AS, sorry, NN and NS. I have a lap joint. We have a bolt connecting this. Now, how many shear planes will be there in this kind of scenario?
One.
One. Okay. That means the minimum number of shear planes to fail, no, for the mechanism to fail. Okay, for the joint to fail. One. Now, typically in this scenario, let's say we have this is the nut. So we don't provide threads throughout. Okay, we don't need to. That's what I'm trying to say. So we can actually have just threads up to this point. So in this case, n will be 0, ns will be 1, right? Number of shear planes passing through shank is 1, and through threads it is 0. Okay, so we can actually interpret that way. For example, but if your bolt is having threads throughout, okay, for some reason, so obviously this scenario will reverse. So we will have n is equal to 1, ns is equal to 0, right? So depending on the situation, you should be able to identify what is nn and what is ns. Number of shear planes passing through the threads, and ns is the number of shear planes passing through the shank, that is without thread.
So
Now,
in any scenario, can this both value be same? Like one, both can
yes,
be?
yes, perfectly. The previous example,
Yeah.
right? The previous example, right? So when you have, let's say, threads are placed up to half point of the shank, like this. Okay, so this fellow will be through the thread, and this fellow will be through only shank.
Yes, sir.
Correct? Yeah. Now, but we don't. This is the shear strength. Okay, design shear strength of the bolt. Okay, so it is nothing but design shear stress into the number of areas it is acting on. Now, apart from that, there are some corrections that are to be made for this one. Okay, so we don't just take it on its face value. So what we say is, say when you have a long joint, okay, for some reason the member is connected like this, a long joint. Okay, maybe the force acting in on it is a lot, but the width available for us is small, so they have placed the bolts in this fashion, so the length of the joint is long. So what is the length of joint? First, length of joint is nothing but, okay, this distance between the two extreme bolts in a, okay, let's say that is lj. Okay, now what is a long joint? First we have to understand, right? So a long joint is typically defined as lj greater than or equal to 15d. Okay, greater than 15d. If it is greater than 15d, d is the we'll have to come to this one. I think that information we have skipped. There is another terminology. D is the nominal diameter of the bolt. Now, what is the nominal diameter of bolt? See, when you have a bolt like this, there are threading here, and then there is this shank is not threaded. D is nothing but this. Okay, the bare minimum diameter of the hole through which it can pass. Okay, it is also the diameter of the shank. But when it comes to the effective diameter or effective area, then you should take the you should take that 0.78 into an, right? So an you will simply calculate as pi by 4 d square. That is the sorry, as. This is the shank, isn't it? Now, but if you are to take the effective area at the threads, we have to use that 0.78 into as. Okay. This is the nominal diameter of the bolt. Now, if the length of the joint is greater than 15 times d, then we say it's a long joint and we have to introduce some correction. So, there are formulae for all these things. Okay, let me just write down. Where is it? Beta Lj is equal to 0.105 minus 0.05 into Lj by d. Okay. Yeah. So this is the correction factor that has to be applied. Okay. And then there is also correction factor for large grip. So yesterday we discussed what is this grip. So it is nothing but the distance between the fasteners that we have, if you are using, or otherwise between the two edges, two innermost edges of bolt head as well as the nut, right? Now, again, this is represented by Lg. Okay, so that what you are trying to say is that, let's say your bolt is too long. Okay, so you have, for some reason, you are connecting very large quantity of packing, uh, uh, connecting materials are too thick. Okay, so this bolt has got a long length, isn't it? Now, obviously, when you have such a long length of bolt, its strength is not going to be very effective compared to a short one. Okay, so we are going to reduce the strength of this bolt in this scenario. See, the reason being, when you have such kind of a scenario, this shank is subjected to bending. It can, okay, depending on the pull and push of all these fellows. Okay, so when there is deformation like this, obviously the strength of the bolt is going to reduce. So that's why we are trying to account for reduction of strength in this kind of scenarios. So what is that? So when you say large grip is when Lg is greater than 5d. So, and then we are going to introduce another reduction factor, strength reduction factor. This is beta Lg is equal to 8 by 3 plus Lg by d. Okay, so this is another strength reduction factor for the shear. Yeah, there is another
So,
one called
so
package.
once previous threads.
Come again?
Previous threads.
Previous one. This one?
No, sir. Next slide.
Next. Okay. Yeah.
Done, sir.
Yeah. Then we have another reduction factor for shear, unfortunately. So what we sometimes have is that we may have to connect plates of different thicknesses. Okay, we may encounter a scenario we have two plates to be connected like this. So in this case, of course, we can use a cover plate and then other cover plate like this, but we have a gap here, so we are going to use something called packing. Okay, this is called packing plate, because we cannot leave the gap and then have a bolt here, right? It has to have some kind of a support. So we use a packing plate like this. So when you have such kind of packing plates, let's say if TPKG is greater than 6 mm, okay, in such kind of scenarios, we'll have to introduce this correction factor. So this correction factor, beta pkg, is equal to 1 minus 0.0125 t pkg. Okay. Now we have introduced 3 correction factors for the shear strength of the bolt, depending on the long joint, length of the joint, grip length of the bolt, as well as the packing material thickness. Okay, if there are certain conditions where these things are large, then we have to introduce things. So when you say, obviously you can see all these factors are less than or equal to 1. So we'll have to simply multiply these factors with the nominal shear strength of the bolt. So now the effective nominal shear strength of the bolt will become, of course, the strength FUB by root 3 into the
Sir,
yes,
sir, here T is thickness of packing plate. No?
yes,
Yes.
yes. TPKG is the thickness of packing plate. Thank you. So NNAN plus NSAS into all these 3 fellows, beta LJ, beta LG, beta PKG. Okay, we are going to multiply them. So whatever the reduction that can happen, so they will contribute towards the reduction in the shear strength. Okay, I hope shear strength is clear.
Yes,
Next,
sir.
let's go to the bearing strength of the bolt. This is probably the easiest thing. But at the end of this topic, I will leave you with a research problem. Bearing strength of bolt. Now, obviously, when you say bearing, so we were talking about this, right? Bearing is nothing but, so let's say there is an area, and then over a small area, there is a force P acting here. Okay, pressure P acting on this one. Now, if this is A, P into A is the relation, bearing force that is coming onto this, right? So we'll have to see, a similar scenario here. So what you are trying to say is, again, design and nominal strengths will be similarly related. VdP will be equal to VnPB. Sorry, this is it should be consistent, isn't it? Okay. Is there a way I can go back? Yeah. PV is equal to VnPB divided by gamma in B. Now, this is the nominal bearing strength of the bolt, and then this is the design bearing strength of the bolt. Obviously, we are going to have a factor of safety. Now, typically, when you say VnPB, the nominal shear strength, so what we'll write is, so we will take what is the area on which the bearing pressure is acting, and then multiply with the strength, the bearing strength of that bearing stress that it can withstand. Okay, so the stress is typically 2.5 times Fu. Okay, so obviously it is more than the ultimate tensile strength of the plate. See, when you say bearing is going to be okay, let's say this is the plate, and then we have a bolt hole. Now a bolt is passing through this. Okay, now when these 2 fellows are in touch, okay, each will exert pressure on the other one, isn't it? So we have to understand from that perspective. So what is the pressure exerted on the bolt? What is the maximum pressure that it can that can be exerted on the bolt? Okay. Now you will answer that very shortly. So let's see this scenario. We have 2.5 times Fu into the area on which this is going to act. Now let's look at the top view of this no, bolt hole from this point. Okay. Now, okay, this is the middle line. If let's say assuming that no, this entire circle, okay, is in touch. Okay. Now the pressure will be acting on this one normally, but we are interested in only in the component in this direction. Okay, so that will be given by simply the D, okay, into whatever the thickness of the plate. Okay, so that's why we have a area of effective area of dt. Okay, now as in the case of shear, we are also going to do some kind of a factor that can actually account for the no, maximum value that it can have. So that is kb. Okay, so kb will define later. Okay, I hope you understood. This is the bearing stress, maximum bearing stress that can come onto the bolt, and this is the effective area coming on no, or through which on which it's going to act, and then this is a factor which will limit the maximum value. Okay, now having understood that, let's write down what is kb. It's a bunch of values, and we just have to take minimum of all these four. Okay, E by 3 d naught, P by 3 d naught minus 0.25, F ub by fu. Okay, I'll come to this, and then 1. Okay, its maximum shall be 1, but uh, it shall take minimum of all these values. Now what is d naught? D naught is diameter of bolt hole. Okay, and we said it shall be more than bolt diameter. Okay, depending on the diameter of the bolts. So we are going to use the bolt hole diameters, and then FUP is the ultimate tensile strength of the bolt. Fu is the ultimate tensile strength of the plate. Now, if you recall, let's go back to one slide before. If you recall, in this formula, we have Fu, which is the ultimate tensile strength of the plate. Okay, remember, the pressure that's coming onto the bolt is from the plate. So what is the maximum it can come? Whatever the maximum it can offer. Okay, that's why we have Fu, not FUB. I hope you understood this point, a very fine point. So we have to take that particularly, especially when the plates and the bolts are of different grade. Okay, if the ultimate tensile strength of these two materials are different, then you have to take the ultimate tensile strength of the plate, not the bolt. Okay. All right. Now, having understood this, okay, let me do some bookkeeping. Now, design tensile strength of the bolt. Okay. T dB again as usual. T NB by gamma MB. This is tensile strength. Now, so what we are trying to say is there are scenarios, especially if you have worked in a mechanical industry, then you will have this kind of huge cylindrical parts to be connected, okay, with flanges like this. So you'll have bolts like this across these flanges, okay. Like I happen to work in aerospace industry, wherein we were a team involved in analysis of these aero engines. So this kind of bolted flanges is a very common scenario there. So these bolts will be under always tension, and as someone has rightly pointed, when you are now trying to use bolts for kind of anchoring, so this will be under tension, so it has to withhold the tensile forces. Now, in this scenario, we should know what is the tensile strength of the bolt. Usually, tensile strength of the bolt is higher. So, V and B will be equal to 0.9 FUB into AN. Okay. So, you can see it is almost 90% of the ultimate tensile strength. So, that's what we have taken as the tensile strength of the bolt. Now, what is AN? This is the effective area, right? Not the shank area. AN is that 0.78 times AS. Okay. So because that will be the weakest section where the bolt can fail. So we have to take the minimum one. So obviously, when you have a bolt or any rod with a section like this, okay. So this fellow will be the weakest one. So we have to take this area into consideration when you are trying to get the strength. Now we cannot take this one. Okay. So this is something like our threaded region, and this is like our unthreaded shank. Okay. So that's why we are taken AN. Now, as we said, the bolt value will be minimum of these three quantities. What are these three quantities? V, D, SB. And then that's the shear component. V, D, BP. Okay. And then T, D. Shear, bearing, tension. So compute these three values and then find out the minimum, then that's called the bolt value. So as we introduced in the first, in the initial point of the discussion, we said, well, if the load is shared equally among them, so we simply compute the number of volts by design load by volt value. Okay. Or design strength of the bolt. Okay, determinants can change a little bit, but more or less we should understand what is the what is the significance of it. Now, there is other part of this story. Okay, so when you say a connection, we don't have just bolts. Okay, we also have these plates, and we also have cover plates. Okay. A connection will be safe only when all these components are safe. If any one of them fail, the connection fails. Okay, maybe your plates are fine and bolts are fine, cover plates are weak, then it's going to rip off and then the connection will fail. Okay, so obviously there are some guidelines on choosing these cover plates also. It should be in such a way that the thickness of this cover plate shall be more than the thickest component in the connection, right? So now what we want to find out, what is the strength of the plate that we are connecting. Okay, so plate, I mean this connecting plate. Now, for this plate, again, we have three quantities that we have to understand. One is
So connecting is that cover plate only, right?
no. See, these are the connected members.
Okay, okay.
Right. So this cover plate shall be having a
Ah,
greater strength,
yes, yeah, got it, got it.
right? So we are talking about now the strength of this connected plate. Now, one is tensile strength or rupture or tearing of the plate. Design tensile strength. Okay, so you sometimes you also call it as rupture. Or tear. Okay. So ultimately, what you are trying to do is that what it takes to just tear off this plate through these bolt holes. That is the weakest point, isn't it? So that we designate as TDN is equal to, again, this is nominal. Okay, so we'll have to use some kind of a factor of safety. FU, 0.9 FU into AN. Okay, now, sorry, 0.9 FU. This is the tensile strength, and then AN. AN is nothing but the effective area that along the plane of rupture. Now, there is a simple formula that you have to remember to find out the AN. Okay. Now, okay, let me pick up one picture that I have. I'll explain with that. So we are trying to understand what is this AN. Now, I'll take the simplest case for which the AN is straightforward. The simplest case is, for example, we have a very regular way of placing the bolts. Now, obviously, this is one weak plane. So if I take a plane passing through the center, oh, plane passing through this center of the bolt holes, obviously, the net section available here will be simply AN is equal to B minus ND naught into T. Okay. Why is that? This is B. And then each bolt hole has a diameter of D naught. And let's say we have such N bolts. So we'll have N D naught. We should deduct that into thickness. Right. So this will be the area available here. This is straightforward to understand. The problem comes if the bolts are not placed in this regular fashion, but we have staggered bolts. So in which case the AN will be given by this formula. Sorry. We'll have to make some correction for this staggeredness. Now let's say the section is going to fail in this zigzag manner because the bolts are placed in this zigzag way. So for this case, we'll have to account for that one. That will be I equal to 1 pi square by 4gi square. 4gi. Now, what is pi? For each of them, what is the pitch? Okay, that is the distance between the two volt source in the direction of load, and G is the gauge between the two volt holes. So we have two cases here. Okay, one is this one and the other one is this. So we'll have to account for both of them. Now, this is the effective area for rupture for regular case as well as when you have a staggered arrangement of the bolts. Now, other one is the failure may not happen here on the plate. Maybe we can think of yielding of the section. Okay, no, the section has simply yielded and then it started elongating like the specimen that you see in a uniaxial test. So in which case, so we say that is the yield strength of the gross section. Okay, that is TDG is equal to AG Fy by gamma MO. Okay, so this is again a shear factor. Factor of safety, sorry. Then we have block shear.
So once can you go to the previous slide, sir?
Okay. Yes.
Sir, here gamma MO is the factor of safety of the plate.
Yes. So we are referring to the plate material, so it will be per plate.
Done, sir.
Yeah.
Sir,
Uh-huh.
sir, in this staggered connection, sir,
Okay.
We add summation of pitch by 4 by J. Sir.
Uh-huh.
Then we can conclude that the staggered connection is superior when compared to previous connection, sir. Because
Yes, it
we
is.
get more area.
Yes, it is definitely. In fact, actually, this is true in many cases. For example, let's say you have designed a building with perfectly rectangular grid of columns. Maybe it is easy to analyze and then solve it. But if you place the columns in in a random way, you can get better strength.
Yes.
So
Sir.
sometimes symmetry is it's not a blessing. It is a curse.
Yes. Sir.
You see, yeah. That's why like I worked on something called homogenization for my possible research. You will find that okay, all the materials that we see have kind of random arrangement. None of them have any kind of regular arrangement. All those fellows who has regular arrangement are very unstable. You see, and you don't find them in nature so easily. And those who are stable and something which are useful for us are always having this kind of a random arrangements. Okay, so if someone is interested in that, and there is a huge topic in structural not structural dynamics, but in dynamics in general. Okay, so you are always encouraged to go into such kind of areas later. Yeah, and then see, this is the strength of the plate, okay, against the rupture, and this is the strength of the plates against yielding, okay, yielding of the gross section. There's one more area that we have to see, which is called block shear, which we generally don't expect that in problems, but we'll try to understand what's the philosophy out of it. Now let's say we have a bracket. Okay, bracket is simply a big plate, and then to which you have connected your or a plate, another plate, okay, carrying the load. Now what happens, what can happen is, maybe the bolts are strong, okay, but this plate can shear off like this, and then it will come out. Okay, so this is shearing, and there will be obviously yielding here or tensile rupture, and this will shear off. So this fellow will move off. Okay, so this is called block shear. That means the shear is happening as a block. So I will not get into that aspect because it's not so highlighted in the exams. Okay, so what we have seen so far is we have seen what is a bolt value. For that, we have seen what is the shear strength of the bolt, and we have seen what is the bearing strength, and we have seen what is the tensile strength. And when it comes to the plate, we have seen what is the tearing or rupture strength or tensile strength, and then gross section yielding. Okay, now so these are all the formulas that we have in bolt and also for riveted joints. So using them, you should be able to solve some problems. Okay, so let's take up a problem and then solve. Right. Okay, let me copy the problem. Yeah. Okay. This is the problem that we have. Determine the strength and efficiency of the lap joint shown. Okay, and bolts are of 20 mm diameter and of grade 4.6. The plate thickness are given to be 12 and right one no. Okay, there is a mismatch, but 12 and 16 is the right information. Okay, they are written as 10 and 12 here, so it shall be 12 and 16. Now, let's go step by step. So, this is printing step. Now, so we were given the bolts that are being used are 20 mm nominal diameter, right? So what is the symbol that we have? D is equal to 20 mm. Now, obviously, okay, the diameter of the bolt hole shall be, since it is 20 plus 2, 22 mm. So it shall be 2 mm more than that. Now, so we are asked to find out what is the strength. Okay, so in order to find out what is the strength, we should be able to find out what is the bolt value and then multiply with the number of bolts that we have, 8. Okay, so let's find out what is the bolt value or the general strength of the bolt. So in order to find out bolt value, so we should find out what is the shear strength, bearing strength, and the tensile strength. So shear strength will be VDSB. Okay, is equal to the factor of safety that we have, gamma MB. MB means for the bolt, right? So and we have FU by root 3, that is the shear stress, permissible shear stress, NNAN plus NSAS, right? This is the shear strength, design shear strength. Now, we have to deduct all these values from the given information. What is FUB? Okay. Now, look at this. 4.6. FUB will be 400. Okay. The information is coded in this 4. Okay. And then, what is the yield strength of this bolt? Let me write that as FYB 0.6 times 400. which is 240, right? So this grade has this information: ultimate tensile strength as well as yield strength. Okay. Now, can someone tell me what is the shear mechanism acting on these bolts? Single shear or double shear?
Single shear.
Single shear.
Single.
Single shear. Now, for some reason, okay, there is no. We can just simply assume, okay, we can assume that the entire bolt is threaded. So when the entire thread is entire bolt is threaded, so we'll obviously the shear plane is going to pass to the threaded region. So N will be 1, Ns will be 0. Correct. Now we have to find out An and As. So first, what is As? Pi by 4, 20 square. That is coming to be 314 mm square. As will be 0.78 into An will be 0.78 into As, which will come to be 245. Okay, I hope you understood this part.
Yes, sir.
Yeah. So we are trying to get information as and when is required. So we completed then. So we can actually ignore this fellow and then simply substitute Nn is equal to 1 and then use the value of 245 as An. And FUB is this 400 from the grade 4.6 information, and FYB we'll use it later, 0.6 into 400, 240. So this is this factor of safety is actually a function of material that we use, isn't it? For steel, so it's going to be 1.25. So now let's plug in those values. We have V DSB is equal to 1.25 into 400 by root 3 into 1 into 245. So this will come to be 45.25 kilonewton. Okay, if you simplify this. Now, that is shear strength. We should find out what is the bearing strength of the bolt. So let's write on the formula. So we have bearing strength, which is okay. Now you see we are actually not doing any corrections here, okay, because we are only talking about the a simple scenario. All those things will not come into picture. The factors of correction factors that we introduced. V dB is equal to 1 by gamma mb into 2.5 kb dtfu. Okay. Now, what is fu? The plates are actually, if you look at the problem, E410, right? This is the information. So we shall take Fu to be 410, right? Now, so we shall to find, this is D is the bolt diameter, which is 20, and then we have thickness of the plate. We had to find out what is kb. So kb is that list of the set of values we have written. So okay, I will leave that as exercise. You can actually plug in E by 3 d naught. D naught is 22. H distance is given. What is H distance from the picture? Can someone tell me? Okay, maybe you are not drawn the picture. So let's go back. What is the H distance? There is 40 and there is 30.
47.
40.
40, sir.
40. Yeah. Okay. And then P by 3D naught. So in this case, P will be 70, right? This is the
70.
pitch. This is the pitch. So we'll have to identify those things. So D naught is 22, we have rightly said. And then what else we have? FU by FUB by FU, comma 1. So we have to take minimum of them, right? So if you substitute these values and then find out what is KU, okay, so that will turn out to be 0.53. Okay, so that you can verify. We have identified all the parameters, right? Now, once you get KB is equal to 0.53 and D as 20 and then T, yeah, there is a catch here. When you are taking this T, you should take the minimum of the thicknesses. Okay. So we have 12 and 16. So we shall take this to be 12. Now you have FU, you have KB, you have D, T, and then gamma MB. Okay. So plug in all the values, you will get this value to be 104.3 kilometer. Okay. Now, I'll leave the discussion for today at the bolt value, and then we'll continue the next tomorrow. Now, I'm not calculating what is the tensile strength of the bolt. Can someone justify that one?
In this case, the primary will be shear and bearings. Tension
Yeah.
won't come in picture.
Tension won't come into picture at all. So you don't have to even care about it now. Okay. So that's why. So when I want to find out what is the bolt value, this one. So what is the bolt value? Minimum of these two, isn't it? So this is the bolt value, right? So what I find is this: always gate is about actually you should have a bigger picture, and but the questions that are going to come in the exam are going to be from the smaller parts of it. Okay, so we'll continue this problem and then solve it tomorrow in the tomorrow's class.
Yes, sir.
All right.
Yes, sir.
I hope we made some considerable progress today compared to yesterday, but still it can be improved, and we'll try to make it as better as possible. Okay.
Yes, sir.
Right. See you then. Good night.
Thank you, sir.